If you don't use the CPU.
Okay, so next one is going to be, Evan Craig is going to be talking to us about tracing containers syscalls using Bpf.
Thank you for coming, everybody. Can you hear me fine?
Yep.
Cool. So I will talk about Inspektor Gadget on traceloop on tracing container syscalls using Bpf. My name is Alban. I am at Kinfolk. At Kinfolk, we do low-level Linux development. We have a Linux distribution, Kubernetes distribution as well, and we do cool things on top of that with Bpf. So today, I'm talking about Strace, Kubernetes, and Bpf. I really like to use Strace as a debugging tool. How many of you like to use Strace? Okay, cool. Like? No? Okay. Well, I like it. Sorry. But I still find it useful. So I like to use it to find out what my applications are doing. So I will present first the traceloop software. What it does is trace system calls, a bit similar to Strace, but done in a different way. It uses C groups on Bpf, and it uses overwritable ring buffers that I will explain a bit later. And then I will talk about Inspektor Gadget, which is kind of something on top to use traceloop and other things on top of a Kubernetes cluster. So traceloop is a command line tool or daemon that you use on one machine, and Inspektor Gadget is on a Kubernetes cluster. If you are interested by those projects, you can join the Kubernetes Slack. There is an Inspektor Gadget channel there. So it uses Bpf. So Bpf basically is a bytecode that you can write your program in C, compile it with C-long LLVM into Bpf bytecode, and you get object file. And you can upload this object file into the kernel with a Bpf system call, and then the kernel will first verify that you don't do anything bad, because this code is running in the kernel, so it will be dangerous if it was cool access to any kind of kernel memory and so on. So there is some verification, strict verification there. And then the Bpf program will be allowed to run and interact sending message to user space through Bpf Map and use some kernel function that are called Bpf helper functions. So that's Bpf in a nutshell, and we will use that for traceloop. So my use case, why do I want to use a Strace on Kubernetes? Sometimes when something crashes, I wish I run that with Strace to see what are the last system call it does. But I cannot use Strace for every application on all the process in production. That doesn't work because Strace is slow. And that's not really the use case, that you cannot do that all the time. If I want to use Strace on only one application that is going to crash to be able to debug it, I don't always know which application is going to crash in advance, so I cannot retroactively start the Strace program. So the idea is to have a system with Bpf that record all the system calls executed by all the applications on Kubernetes, and record that in a ring buffer. It's an overwritable ring buffer, so it's, when it fills the ring buffer, it's overwrite the previous events. And then this ring buffer is there in memory, and if a pod crashes, your application crashes, then you can ask, oh, what were the last system calls that were recorded in the ring buffer? So here I compare Strace and traceloop. That works differently. Strace uses ptrace. The granularity is one process, one or several processes. And traceloop works with Bpf on trace points. The granularity is C group, so I can select the C group where I will get the traces. Strace is kind of slow. You cannot really use it for all the process for everything. But traceloop is fast because we don't actually read the system calls events. Only when something crashes or when the user asks for it, we get the last system calls. And finally, Strace is reliable. It's synchronous, so it's you cannot lose events. All the system calls that are done by your application will be printed by the Strace command. It will not forget some. Traceloop is not like that. It's possible that some events are lost because it uses a ring buffer, and if you miss some events, then that happens. And sometimes you might not always get the parameters of the system calls as opposed to ptrace using the method with Bpf. In some case, you might not have all the information, but that's still very useful and good enough. So what I do with traceloop is to add a trace point on the sysenter trace point on Linux. So every time we enter a system call, this trace point will be triggered and execute this Bpf program. And this Bpf program will decide what to do with that system call. It will first look in which cgroup it is, in which pod or which container, and then depending on the container, it will redirect the execution program to another Bpf program. So it uses Bpf map of a special kind called program map, and depending on the cgroup, it will redirect the execution to a different module and log the system calls in a different ring buffer. Those ring buffers are configured to be overwritable, so that's not the default on perf ring buffer where it's stop writing when it's full, but those one is just overwrite continuously. And then when the user asks for it, the user can read the last system calls, the last few system calls. So I can do a demo of traceloop on a command line. So traceloop is a CLI command line tool. Is it big enough? It can run as a daemon, or it can run on the command line like this. Here I will specify you will trace whatever process is in a SSHD cgroup. So let's try this. Okay, now it starts to trace. So I will generate some traffic on SSHD. I want to make it do some system calls. Okay, so now I did some system calls. As you see, you don't see any trace here because it doesn't actually look at the ring buffer. Only when I ask for it, we are here with Control-C, I will get the last system calls from SSHD. So I see it does some socket system call like receive message, select, and so on. And the last few system calls are printed here, and I can debug my application. Okay, so that was traceloop on the command line. Now I want to adapt it to Kubernetes. So what do we want for Kubernetes? We don't really want the user to SSH to a node. Usually the user doesn't really care about PID or cgroups, but they care about Kubernetes pods or Kubernetes labels. So you want to be able to select the thing to debug with a pod or the labels. And then the user experience should be something close to kubectl, which is the command line tool for Kubernetes, and not having had to SSH on the node. It turns out there are already Kubernetes tools doing that. So on the left side, I have some Bpf tools, Bpf trace, BCC, and traceloop. On the right side, some Kubernetes level tools that use the tools from the left. So that's a really cool project. For example, kubectl trace can use Bpf trace on a Kubernetes cluster. And Inspektor Gadget use BCC and traceloop as well. Basically, it works like that. When you're on your laptop, you use kubectl Gadget, which is client-side plugin to kubectl, and then it will issue some API calls to Kubernetes. It will not do any SSH or any other things. It will only go through the API server and request some BCC scripts or Bpf program to be executed on the node. So now it's time for another demo of traceloop on Inspektor Gadget. So here I have some Kubernetes pods running on. What I will do, I prepare here a command to run, which will start a new pod with some shell scripts here. So I run my pod. It computes a multiplication here. And then didn't write my shell script correctly, so I don't see the result. So, but I still have a way to debug it. Even if I delete the pod that I just used, I have 10 minutes left. I can, my pod is gone because I just deleted, but with Inspektor Gadget traceloop list, I can see the list of the last few traces. And I should be able to find one, which is this one, 28 seconds ago. I will do Inspektor Gadget trace loop show on this. And I should be able to see the last system call that were recorded in the rig buffer. So I can see, for example, that this, the BC process and the shell process were doing the multiplication and printing the output, but so I can debug my application here. Okay, so I will show some stop gaps in traceloop that are things that I implemented in traceloop, which are not the perfect way, but I will explain why. So initially, I wrote Inspektor Gadget for Kinfox Linux distribution, that's Flatcar Container Linux on Kubernetes distribution. But then I wanted to make it work on other normal, older Linux kernels, for example, like a Minikube or GKE use 4.14, which doesn't have all the Bpf feature I wanted. So for example, it doesn't have this Bpf helper function I wanted. It doesn't have cgroup version 2 enabled by default. And there is no proper way from Kubernetes to use OCI hooks. But still, the traceloop program works on all those Kubernetes distributions with some hacks or workaround or stop gaps. So instead of using the get current cgroup ID, this Bpf helper function that is not available on older kernels, I use some custom way to get the ID of namespaces, or Linux namespaces, and then I find that to identify which container I am looking at. I don't have OCI hooks, so I cannot add a new module, Bpf module for each pod at the beginning of the container. And I cannot really use the Kubernetes API to discover a new container because that would be too late. By the time I get the notification from the Kubernetes API or for the Docker API, the container is already running, it's already doing some syscalls, so I will not catch the very first system calls. So that was an important use case for me to be able to trace the very first system calls, because maybe this container crashed in the very first second, and I want to be able to debug that. So instead, I have a pool of Bpf modules that are preloaded, and dynamically in a Bpf, I link them to a new cgroup as they appear. At this time, I don't really know yet which Kubernetes labels they are, or which pod, which container they are, but I will reconcile that a bit later when I get the notification. So far I talked about traceloop, which is one gadget of Inspektor Gadget. There are other gadgets for different use cases, some for debugging your applications, some IDs which are not finished yet, it's work in progress. I want to be able to see what network connections my pod is running, and be able to help a developer to write network policies. Yeah, it's like doing security as an afterthought. Sometimes we develop an application, we think about security later, and then we think, oh, we should maybe add some network policies or some PSP or something like that. But when the application is already developed, we forgot other architecture, and it's kind of useful to discover what it's doing and suggest to the developer network policies. So that's not finished work, but that's something I would like to have. I will just do a demo of exec-snoop on OpenSnoop. There are tools that come from BCC, so I just took the BCC scripts. So I have the same Kubernetes cluster, and here I run Inspektor Gadget exec-snoop, and I will specify the label of the pod I want to trace. And here on my 3-node cluster, I will get every new process that is executed with, I will see that with exec-snoop. Okay. I have the same thing with OpenSnoop. It does trace every time I open a new file. So since I run some shell script, it uses libc and so on, and it opens different files. Okay. To be able to do that, I use something I call the Gadget Tracer Manager. These are the things I want to be able to filter on. So usually I don't want to filter to get the information from all the pods always, but I will select either with Kubernetes label or on a specific Kubernetes namespace or a pod name or node or container index when there are several containers in the same pod. So there are all the different ways to filter things. Filtering by label is quite important to me because usually when you deploy a pod using a deployment on Kubernetes, you don't know in advance what is the name of the pod because Kubernetes creates the name with a random suffix. So I don't know the name of the pod in advance, and if I want to trace the very first system call, I need to be able to filter in other ways. So I use labels. So pods can come and go. I don't know their name in advance. And a tracer can come and go too, and I need a system to link them together. For example, this tracer will get this information from those two pods, but not the third one, and so on. So for that, the Gadget Tracer Manager is just a daemon which has a gRPC API and some method to add or remove containers or tracers. So here I use OCI hook restart. Every time there is a new container, I tell the tracer manager that there is a new container, or when one stop. And when I run Inspektor Gadget with some gadget, it will tell the Gadget Tracer Manager that there is a new tracer or one is stopped. And what the Tracer Manager will do is to update Bpf Maps. So there is one for each tracer, and this map contains the list of cgroups that the tracer should trace. So the list of containers, basically. And then when I run BCC scripts, like exec snoop, I will specify which Bpf map to look at to know which cgroups to trace, basically to know which pod or container labels I want to trace. So if you want to contribute to those, I just created a couple of labels. So there are some issues with a good first issue label on GitHub. That's things that are a bit more easier or I'm able to help. And there is this new Inspektor Gadget Slack channel that you can join, and we can talk there as well. Thank you. So now I can take questions.
Yep.
So Alban, you mentioned your locomotive distribution. So what do you need? Would you need that for? Is there anything you can do with that? You cannot do with anything else?
So it doesn't have anything magic. That's just normal Linux technology. Traceloop works on others or older kernels as well. But for the other gadgets, I need the latest Bpf helper functions, such as get cgroup current ID, and I need I did some hack in runc to be able to add or remove OCI hooks. They are work in progress in Cryo on containerd, I think, to be able to configure that. But at the moment, it's done in a hacky way until we get that upstream. So there are, I use cgroup version 2 as well, enabled by default. So each container is in a different cgroup version 2. Which might not be the case if you are running other Kubernetes distribution. But although all of that, they are Linux technologies, so you can enable them elsewhere as well. There is nothing really specific to locomotive or Kubernetes distribution.
Okay, out of time. Thank you.
Thanks.